liking that inquisitive. I'm looking at your calculator way. So we're just going back to what we do with parabolas, and we're going to look at graphically. We're going to compare x squared to 5x squared to 1/5 x squared. Nothing should be surprising here. We know what's going to happen. So go into your y equals. If you've got stuff in here, clear it out. So x squared into y1, into y1 perhaps. Jump down 5x squared, and then jump down 1/5 x squared. How do we get the graph to appear? Who remembers from last year? We don't press graph because we don't know what the axes are set up like. I always go to a different button. What do I go to? Zoom, remember this from last year? And we pick, which one looks familiar? Zoom standard number 6. What that does is set up your axes -10 to 10 in each direction. Okay, so the one in the middle was our base parabola. The one that's close to the y-axis is that vertical stretch. So someone has grabbed the top and yanked it. That's why it's skinnier. The widest one is elephant has come and sat on our parabola, so it's squished down. Okay. Let's look at your first horizontal stretches. Go back into your y equals. I'm going to clear out y2 and y3. I'm going to keep my y1 for now. And this time I'm going to put the brackets in. So I'm going to go bracket 4x bracket squared. And let's compare that to bracket 1 divided by 4, or 1/4 x squared bracket. And zoom standard, and they'll come in order. So base parabola, skinny parabola, wide parabola. So the one in the middle is the normal parabola. The skinny one, that's your horizontal compression. We have squished it in from side to side. The wide one is a horizontal stretch. We have yanked it out side by side. You notice they look very similar. Okay? A vertical stretch can look like a horizontal compression. A vertical compression can look like a horizontal stretch. So they have kind of a similarity to them. Questions so far? What do you notice here with the vertical compared to the horizontal? Brackets. The vertical is outside brackets. It's out in front of the function. Where is the horizontal stretch or compression? Do you see a theme happening here? Anything outside brackets is vertical. Anything inside brackets is horizontal. How do you tell a difference between the three things we've done? Well, if you're adding or subtracting, that's a translation. If it's a -1, so there's a negative in front, that's your reflection. And if it's a multiplication or division, that's a stretch or compression. Okay, let's just draw some ideas here, grabbing my colors. So I'm just going to generally call this number a. What does a mean? Any number. And this is 1 divided by a, so it's our fraction. So this is our base parabola. What's happening with this one is this is a vertical stretch. Again, mathematicians, obvious people, VS, vertical stretch. And this is somebody yanking on the top, so grabbing the two pieces and yanking it upward, and that's why the graph becomes skinnier. And last year, you're probably thinking, well, if it's a big number, shouldn't it get wider? Because bigger means wider. Not in this case. It means a vertical stretch. You've yanked it. That's why it's become skinnier. 1 divided by a, so it's a fraction. That is a vertical compression. Vertical compression. Compression means that something has come and sat on this parabola. It's compressed it from the top or bottom, and that's why it became wider last year. Okay, so flattens out because something's sitting on it. Vertical compression. The horizontal ones we didn't do last year because you weren't ready. Now you're ready. And I've called it B just because I didn't want to call it A, so don't let the letters freak you out. It's just a number that happens to be in front, or in front inside the brackets. This is a horizontal compression. Horizontal compression. And so this is pushing it in from both sides, pushing it in from the left, pushing it in from the right. And so the graph gets skinnier. And if you notice up top, vertical stretch, horizontal compression tend to look alike. But this one we are changing the y coordinates, this one we are changing the x coordinates, and we'll talk about that again in a second. Anyone want to guess what 1 over b, so a fraction inside the brackets, is? What's left that we haven't talked about? Horizontal stretch. And that is where you're grabbing the sides and pulling them outward. And if we grab the sides and yank them outward, what's going to happen to our parabola? Wider. And again, if we compare the vertical compression and the horizontal stretch tend to look alike because they both have a flattening effect. This is affecting your y values. This is affecting your x values. So it's just changing a different part of the point. Okay, there's some theory. Let's talk about the how do I graph this, what am I doing stuff. So vertical stretches and compressions, horizontal stretches and compressions. Where are my left brain people? I want to invent some kind of highlighter that's got like a built-in straight edge so it always highlights straight. That would just make my world. Like I could make $1 bajillion off of that. Did I tell you my other retirement plan? Was I telling you this? Okay, wait, let me tell you. Back to stretches and compressions. This is just formalizing what we talked about on the other side. So when A is bigger than 1, what's that saying? It's a number that's bigger than 1. It's 2, it's 3, it's 4. This is called the vertical stretch. Zero less than A less than 1. What does this less than A less than notation mean in English? Yes, you're just a step ahead of me. Just this notation itself means between. So this is saying between 0 and 1. What kind of numbers are between 0 and 1? Fraction. So this is mathematically saying if it's a fraction between 0 and 1, it's our vertical compression. Now somebody usually thinks at this point, well, what about the negatives? These are positive, these are positive, what are negatives? Negatives are reflections. We did those last class. The negative is what flips it either up and down or flips it side to side, so we don't need to worry about them here. To sketch the graph, this is the key, so I'm going to switch to red because this is super important. What you're going to do is multiply the y coordinates by A. Whatever that number happens to be, you're going to multiply the y coordinates. Why the y coordinates and not the x? Because it's vertical, and all things vertical affect y, because it's the y-axis that's vertical. So we started talking about this mapping the other day, and the mapping is just taking this sentence and putting it into notation. And so the mapping xy goes to, x stays completely the same. We don't touch x with anything vertical. And we call this ay. We multiply the y's by a. Okay, horizontal. When B is greater than 1, it switches. That's a horizontal compression. So just look at the difference. When it's 1 up here, it's a vertical stretch. When it's 1 down here, it's a horizontal compression. 0 less than B less than 1. Again, this means between 0 and 1, and numbers between 0 and 1 are fractions, so it's a fancy way of saying a fraction. That's our horizontal stretches. You know how the horizontal things kind of have that backwards feeling? Remember with translations, when the number's positive, we move to the left, and when it's negative, we move to the right. It's got kind of that backwards feel. Same idea here. We're not going to multiply. We are going to divide. Divide the x coordinate by b. the mapping xy goes to bx, y. Multiply the x by b, don't touch the y value. Lefties understand my need for white O's. Right brains are scribblers. We tend not to be scribblers. X divided by b, y. Ooh, that says x, but you can't really see it. It still says x there. What I like about this unit is it's very logical. So anything outside the brackets is always vertical. Anything inside the brackets is always horizontal. There are no exceptions to that. That is always true. If you're adding and subtracting, it's a translation. If it's a negative, it's a reflection. If you're multiplying, dividing, it's a stretch compression. That will always be true. And we're going to talk about all of that again tomorrow, next time I see you, when we talk about all of these in one. But we're just going to focus on stretches and compressions, a little bit of reflections, a little bit of translations. Okay, below is the graph of f of x. Sketch the graph of negative 3f of x. State the domain and range. Casey, you're on top of that domain and range. Not in charge anymore, no. So this is one where they're not saying to you it's a parabola or it's a cubic or an absolute value. They've given you this funky graph and they're telling you what to do to it. Okay, so we don't need to draw the base graph. They've done that step for us. We need to start with identifying the transformation. So I'm going to go in order. The negative outside the brackets. Well, because it's outside the brackets, that tells you it is vertical. Because it's a negative, that tells you it is a reflection. This is a vertical reflection. And so the mapping says that xy goes to, with vertical, we never touch the x's. What do we do to y? Negative y, which means change the signs of y. Well, let's actually draw that before we talk about the next one. I'm not going to go to red because this is not our final graph. I'm going to pick a different color. I'm going to pick green because it just called out to me. Now, we don't have coordinate points, but if that's still your method, you can pick some points and write them down. I'm going to go right off the graph. So I'm going to pick this point here, and that point there, because they're really nice points that cross the axes at good points. They're not decimal values. And all I'm going to do is exactly what the mapping said, is I'm going to take the y values and change the sign. So this first point, what are the current coordinates? 2, 0. And if I change the y coordinate, it becomes 0. So that point stays exactly the same, which is kind of nice. What about this little bump here? It's the little vertex of this little parabola piece in the middle. What are the current coordinates? 0, negative 4. So they're going to become 0, 4. And 2, 0 is going to become 2, 0. So I know that little bump now is going to be above the x-axis instead of below because I did a vertical reflection. What about these pieces on the side? Well, if they are currently below, what's going to happen to them? They're going to flip up. So I'm just going to eyeball them. There's my vertical reflection. If you would have rather multiply or write those out as a table and then show the new coordinates, that's fine, however your brain needs to do it. Now let's talk about the 3 that's tucked in here. It is outside the brackets. Automatically, you know it's a vertical something, something. How do you know what it is? Well, is it adding, subtracting, a negative, or a multiplication or division? So what is that 3's purpose? What are we doing with him? We're multiplying, because there's no plus sign in there. There's nothing going on. It's a multiplication. If it's a multiplication, that is a vertical stretch. Okay, so a number outside the brackets that's not a fraction is a vertical stretch. The mapping says xy goes to, because it's vertical, I'm not touching x, and all I'm going to do is take all the y values and multiply by 3. I'm going to use red because this is my last graph, and I'm working off my green graph here, not the original, so I always go step by step. And I'm going to use these same 3 points because they worked well the first time. The y value of this point is 0. 0 times 3? 0. Well, that's handy. It doesn't move. The middle point is 4. 4 times 3? 12. So off the graph, actually not quite off the graph, very top of the graph. And that third point, the y value is 0. 0 times 3? 0. Okay, so let's do that middle hump first. Whoa, look at that. Why did it go so far up? Well, again, imagine your giant grabbed that little loop and yanked it up. What's going to happen? It's going to go way up. What about these pieces on the side? If they grab them, what are they going to look like? Slightly skinnier, just like a regular parabola. So I'm just eyeballing them because I don't have exact points. Look away. Look back. Did we flip this over the x-axis, and did we yank on it from the top? There's your first stretch or compression. So remember when we graphed parabolas last year, we had the vertex width direction, and that width we talked about being 135 ... But then if we had a number in front, we crossed it out, we multiplied. This is what you were doing. You just didn't know it. You were multiplying the y values by whatever that value was. So when you went to 2 and said 135, 2, 6, 10, that's because you were multiplying. So we were doing it back then, you just didn't know it. Okay, here's a typical question where it actually doesn't ask you to do any graphing, it's just asking you to change the equation. So the graph of f of x equals x cubed undergoes a vertical compression of a third, a horizontal and vertical reflection. State the equation after these transformations. Grabbing my highlighter, what are some key things that we need to know in this sentence? You're so in charge now, Nick. You are in charge of domain and range. Good job. I always forget about it. Domain, look to the left, look to the right. What does it mean when these pieces just keep going forever and ever and ever? XCR, if you prefer that notation. If you like the other notation. The range, look down, look up. What's the lowest value of the graph? And again, we're going with the red one, the last one. Where does it stop? 0. Where does it end? Infinity. So if we want to match this notation, that's matching this one. Y greater than 0 or equal to, because there's actually a point right on 0. If we want to match this notation, 0 to infinity. 0 with the square bracket. And not a little dot there. That's nothing. Don't look at that. Because there's a dot at 1, so it's equivalent to the or equal to. Round brackets means close to, but not including that value. Now we can go to this one. Bless you. Bless you again. Okay, what's important? What do you want to highlight? The function, usually important. What kind of function is that? It's a cubic. How do you know it's a cubic? The cubed. State the equation. Vertical compression of a third, inside brackets or outside brackets? How do we know it's outside? Because it says vertical. So I'm going to leave that y equals. I'm going to have my x. I'm going to put some brackets around the x, and I'm going to put my cubed. And then we're going to put everything either inside or outside. Vertical compression is outside, so my 1/3 is going to just tuck in front. Horizontal reflection. Horizontal means it is inside. How do I display a reflection? It's just a negative, so I'm going to tuck a negative in front of the x. Vertical reflections are outside, so I'm going to tuck a negative out front. And then because I'm left-brained, I'm going to rewrite it and make it look prettier. And right brains probably don't care. Let's just double check. Negative out front is a vertical reflection. Do I need that? Yes. A fraction out front is a vertical compression. A negative inside is a horizontal reflection. Good to go. This is what the question is asking you for. Just give me the new equation, don't graph it. Woo, square root graph. And I gave you the base graph, save you some trouble there. Nick, state the domain and range when we're done, okay? Remember yesterday, I was like, note, there was a little condition with a horizontal reflection. What was that little thing? We wrote it in red, we put a star, I said you have to do something with a horizontal reflection. Kind of. Flip back in the notes and see if you can find it. It should be red with a star, maybe highlighted depending on your brain. There's something like, no, there was a trick with horizontal reflections. You had to factor. You have the same trick here with horizontal stretches and compressions. So we're going to put a star. I'm doing it in red. And I'm making a note. With horizontal stretches or compressions, you must factor if possible. Here's why. If we just took this at face value, we're going to say, okay, a 2 inside brackets horizontal, whole number compression, translation 4 units to the left. Watch what's going to happen when we factor. All I'm going to do is I know there's a common factor of 2, so I'm just going to take them out front. And so 2x divided by 2, x, 4 divided by 2. So it's not actually 4 units to the left, it's 2 units to the left. That's why you have to factor, because it's going to screw up your translation. Okay, so let's identify. The 2 is inside that or inside the radical or inside with the function, so it's horizontal. Because it's a whole number, it's a compression. And the mapping says that xy goes to, with horizontal, what do? We divide. So x divide by 2, y. If your brain would rather write this as 1/2 times x, if that looks better to your brain, then write it as 1/2 of x. It's the same thing, whether you divide by 2 or you multiply by 1/2. Okay, let's talk about the 2 here inside the brackets. Because it's inside, it's horizontal. Because it's adding and subtracting, it's a translation. And this is going 2 units to the left. If you would work off the table of values, do that, because you know what the base points are. You know it's 0, 0, 1, 1, 4, 2, 9, 3. So if you'd rather work off that, work off that. There's nothing wrong with that. Horizontal compression, I'm going to take the x-coordinates and either divide by 2 or multiply by 1/2. It's totally up to you. So I'm going to start with 0, 0. So 0, 0 goes to 0, 0. Well, that's really handy. 1, 1 goes to 0.51 or 1/2 1. So I'm going to go 1/2 a box over, 1 box up. 1/2 a box over, 1 box up. I'm going to ignore 2, ignore 3. We've talked about before because they're not nice numbers for y. I'm going to go to 4. And the original point is 4, 2 goes to 2, 2. That made me laugh. 4, 2 went to 2, 2. What's the next point I'm going to use? So after 4, we're going to go to 9. 9, 3 goes to 9 divided by 2, which is 4.53. If your brain is like, what the heck just happened, then write them out, because it probably means you're visual and you just need to see it. Join them in a little swoop. Did something come along and smack the side of your swoop and make it squishy? Did they squish it in towards the y-axis? Yes, that's why it looks like it got higher. It's just because it's squished in. So imagine that's a pipe cleaner and you push on it. It's going to get squishy. Going to red pen because this is going to be our last graph. Going to the orange graph for me, not back to the original. We're always working off the last graph. What are we going to do with it? We're going to pick it up and move it 2 units. Look away. Look back. Did we squish this thing in from the side, and then did we move it over to the left? Show me your thumb so far. What we're doing, good. I kind of get it. Good. Domain and range. Oh, I put note down here, but I wrote note up there. I got overly excited. The notes for the note. Domain left to right. What's the smallest value to the left? -2. What's the highest value on the right? Infinity. If you like the other notation, something with -2 greater than or equal to. Range, look down, then look up. What's the lowest value on the bottom? What's the highest value on the top? If you want to match the other notation, we got to have y and 0. What would the sign in between be? Greater than or equal to. Ooh, absolute value. Yeah, love it. What's the shape of an absolute value? It's the V. So we're going to have a V somewhere in here. Ignore the numbers. Draw the base graph. Give me some points on the absolute value graph. 0, 0. 1, 1. -1, 1. Give me some more. Give me some more. Yes. One more, just for fun. Again, if you like to write those out, then feel free to write them out. There's nothing wrong with that. Okay, let's identify the transformations. Working from left to right, I'm going to start with the 4. It is outside brackets, so that tells you it's vertical. It is a whole number, so that tells you it is a stretch, vertical stretch. The mapping, xy goes to x 4 times y, 4y. Okay, I'm going to do it with the points this time just in case people like to do that. If you can work off the graph, then go and work off the graph. So I'm going to take the y's and multiply them by 4. So 2 becomes 1 becomes, 0 becomes, and 4 and 8. And then I'm just using the original coordinates, so -2, 8, -1, 4, 0, 0, 1, 4, 2, 8. I like the absolute values because to me it's really easy to see we've yanked this thing upwards. Am I going too fast? No, we're good? Okay, I'm going to go to this 2 that's inside the brackets. It's inside, that means it's horizontal. It's a whole number, that means it's a compression. XY goes to x divided by 2, comma, y. And again, if your brain would rather have 1/2 times x, write it that way. It's the exact same thing. For the interruption. If you're a point person, it means we're taking the x's and dividing by 2 or multiplying by 1/2, whichever makes sense. So -2 is going to go to -1, -1 goes to -1/2, 0 goes to. Do you see why the origin is such an important point? Because what happens with most transformations stays the same. That's why it's such a good point for us. 1 times 1/2, or 1 divided by 2 is 1/2. And 2 divided by 2 is 1. So now I'm plotting these two outside ones. If you're just working on the graph, I'm going to the green graph. And I'm going -2 goes to -1. You notice I didn't move that up and down. I just brought it in towards the axis. -1 goes to 1/2. 0 goes to 0. 1 goes to 1/2. And 2 goes to 1. Okay? Didn't move any of those points up and down. I just moved them side to side. Look at, for me it's green, whatever your second one was. Look at the red one. Did you squish it in from the left to the right? I squish your face. Squish your face. Look away. Check it out. Look back. Look at the original graph. Did we yank it upward and then did we squish it in from left to right? Really squishy absolute value there. How are we doing so far? Good. We've done the radical, we've done the absolute value. The last one is our cubic, our friend. Oh my God, lots going on in this question. So if your brain's like, too much, just worry about the base graph. Draw that first. What does the base graph of a quadrat or a cubic look like? So if you need the points, we can do the points. If you don't need the points, don't need the points. -2 cubed. -2 times -2 times -2, -8. -1 times -1 times -1, -1 cubed. 0 cubed. 1 cubed. And 2 cubed. Okay. If you just remembered those, you don't have to write those down. It's up to you. If you can go straight to the graph, great. What's the shape of a cubic graph? Yeah, like a snake. We're going to come back to cubics in unit number 4. Okay, so if you look at this and you're panicked, you're just going to work from left to right. So all I'm going to do is look at the 2. I'm not even going to look at the rest of the stuff because it freaks me out. Let's just look at the 2. First question you ask yourself, is it inside brackets or outside brackets? Then you know it's a vertical something. Is it a multiplication, an addition, subtraction, or a negative? Multiplication, addition, negative. It's a multiplication. Is it a whole number or is it a fraction? So that tells you that it is a vertical stretch. XY goes to, remember with vertical we never touch X. And what do we do when it's a stretch? We multiply 2Y. And again, the point of the mapping is just to help you to figure out what are we doing into what coordinate. Do you want to identify them all first and then draw them all, or do you want to identify one and draw it, then identify, then draw? Identify all? Okay, now I start going inside this bracket, and the minute you see horizontal stuff going on, you ask yourself, do I need to factor? And you'll know because there's something in front of the X. If there's something in front of the X, you're probably going to need to factor. Do we need to factor? What do we need to factor out front? Negative 3x divided by negative 3, x, and positive 3 divided by negative 3, negative 1. And then I'm closing off and keeping my cubed. The factoring is important because look what it did to that horizontal translation. It took it from 3 units to the left, and it's really 1 unit to the right. That's why the factoring is so important. Okay, again, just working left to right, I'm going to look at the negative first. And you'll notice the negative is different from the 3. Those are 2 different transformations. It's inside bracket, so it's horizontal. The negative tells us it is a reflection. Mapping says that xy goes to, well, if it's horizontal, we're touching the x's. And because it's a reflection, what are we doing to them? Changing the sign, so negative xy. The 3, it's inside bracket, so it's horizontal. It's a multiplication, so it's a stretch or compression. It's a whole number, so it is a compression. XY goes to, horizontal means we never touch the y's. And if it's a compression, we divide by 3. And if your brain would rather write that as 1/3 x, then write it that way. Oh yeah, we're not done. What do we still have here? The negative 1, bringing you way down here. It's inside brackets, so it's horizontal. It's a subtraction, so it's a translation. And it is 1 unit to the right. Ready? This is good stuff. I love this. Okay, back up here in our vertical stretch. We're multiplying the y's by 2. If you just want to change the coordinates, whatever makes sense to you. I'm going to go off the graph. Negative 8 times 2, way down here somewhere. So I'm not actually going to put like a real point. I'm just putting a little dot just to remind my brain it's way down there. The next y is negative 1. I'm sorry. Negative 1, correct. Negative 1 times 2, 3, what are we at here? 2 times 2, negative 2. 0 times 2, love the origin because it always stays. 1 times 2, 2. And 8 times 2, like way up here somewhere, so I'm just putting like a little dot just to remind myself it's way up there somewhere. So I know it's going to curve through these 3 points and go up somewhere. Some brains, usually left brains, like to number. So if you want to number your transformations just to remind yourself later which is which, do that. If that's not for you, then don't do it. Horizontal reflection. So tactile people, what I do with my fingers is I go like this to remind myself horizontal reflection. I'm flipping side to side. So I know I've got to go from the left to the right, right to the left. If you want to work off the points, you're just changing the sign, so whichever one you want to do. So I start down here and I say, okay, if this is negative 2, I'm on the orange one. Negative 1, negative 2, it's got to flip over, so it's going to go to negative 2, positive 1. So I just flipped it over. The origin stays. And this other point here that's at 1, 2 has to flip over to negative 1, 2. Again, if you want to work off the points, work off the points. Okay, just remind yourself we're doing a horizontal reflection. We're flipping from left to right. And so this was number 2, and this was number 2. Tactile people, I go like this. Horizontal compression. I remind myself we're squishing this in from side to side. It's got to go squishy. It's not going to stretch. Squishy. Okay? We're taking the x values and we're dividing by 3. And 3s are sometimes hard because we're going to have thirds. We're just going to deal with it. So I'm now working off my dark blue one. And we're looking at the x values and we're squishing it in. Negative 1 would become negative a third. Okay, so I didn't move that up or down. I just am squishing it in towards the x-axis, negative a third. And I'm estimating a third of the box. 0, 0, yay, doesn't change. And 1 goes to 1/3. Squish it in towards that x-axis. Last one, so it's in red, and hopefully you can start to see now why I need the last one in red, because if you've made a mistake in here, it's almost impossible for me to find, where if it's in red, I can try to get you some partial marks. Translations, we're just picking up and moving it 1 to the right. So I'm going to grab my 1/3 2, and I'm going to move it over 1 spot and keep it at 2. Okay, so it's now at 2/3 2. The origin is just going to move 1 to the right, so it's at 1, 0. And my 1/3 negative 2 is going to become 1 1/3 negative 2. That's as hard as the questions are going to get. That's about as much as we'll put into one question on the exam. So that was 5 different graphs, 4 different transformations. This is why I said don't try to do too much in one step. If you're trying to do more than one of these in a step, it's really hard to miss where the points are. If you go step by step, it's easier. I think that's it. That's it. No domain and range. We're good to go. How are we feeling? Show me with your thumb your thoughts on